I can start.
Okay, so yeah, so we are very happy to have Michael Kroyter here today, and he will speak on his latest work, I guess, on democratic string field theories with Stefano Giaccari.
So Stefano is also here, I see, so I'll start. And okay, so I'll introduce some stuff and then I'll introduce some more stuff, which will be the old democratic theory. So the whole construction is based on an old theory. I mean, not so old, maybe. I'm also not so old. Okay. So the construction is from 2009. And I know that some of the people in the audience already heard me talk about it much more than what they would like to hear, and others didn't hear about it at all. So I had basically three options. One was to make a very long introduction, and then many of you will be very bored. And another would be to just skip it all and assume that you know, and then some of you will not understand anything. Or I could take the middle ground, and then some of you will not understand anything, and the others will be bored. So eventually I decided to go on the direction of a long introduction. So I apologize to all those who already heard everything that I have to say now for way too many times. And let me start. Okay, so what do I mean by a democratic theory? So I mean by that a theory in which all picture numbers are present, and this construction relies on an alternative formulation of the cohomology problem of the open superstring that Berkovich introduced a few years before this work. And this will be the only reference that I'll put, and I apologize for it for everyone whom I should have mentioned. Now, in this approach, picture changing becomes a gauge symmetry. The theory is cubic. It lives in the large Hilbert space, and it relies on a single midpoint insertion in the action. Now, the theory looks very nice. I mean, it looks natural. It elegantly unifies the Ramond sector. The BV classical master equation is also formally very straightforward. And you can take partial gauge fixing, so fixing the picture number, and that would lead to other consistent formulations that we know. But regardless of all that, this did not play any role in all the very nice recent developments, recent from the last, say, 10 or so years. And why? And the reason is, of course, that as many of you told me, there are problems with this theory. And some of the problems that are mentioned here, that were mentioned, are that, well, what is the space of string fields? There is a very delicate issue there. There are problems with the midpoint. So presumably, so the fact that I'm using an insertion at the midpoint is problematic. There are zero momentum operators, that is string fields of arbitrary negative conformal weight, even at zero momentum. And this is quite unnatural. Then the theory relies on operators XP and OP, which are only implicitly defined. And the last thing is that it is not clear how to gauge fix, in particularly how to fix the picture in a consistent way, and to obtain from it a propagator and then do everything that we like to do with a theory. And if anyone here has any other criticism which I forgot, it would be good if you will mention it, so I'll be able to maybe discuss it as well. And also, of course, if anyone has any questions at any stage, just stop me and I'll try to answer. Okay. So how do we normally formulate a string field theory? So the normal way is to identify the worldsheet cohomology problem as the first step. Then we want to extend the vertex operators off shell, so we will have string fields. We reinterpret the cohomology problem as defining equations of motion and a gauge symmetry. And we try to derive everything from an action, the equations of motion, the gauge symmetry, and Then we add interaction terms, so the equations of motion and the gauge symmetry become nonlinear, and that's the standard thing that we do. So what is the cohomology problem for the open RNA string? So we can live in the small Hilbert space, and I'm considering for now just the Neve-Schwarz sector. And when we are at any fixed picture number, this would be our equation of motion at the linearized level. That would be the for the cohomology problem. So this will be the what will become the linearized gauge symmetry. And the picture number is arbitrary, and we have to restrict ourselves to ghost number 1. And we know also that we can work in another formulation. So in the large space, we can fix the picture number arbitrarily, and then the equation of motion will be that at the linearized level, and this will be the linearized gauge symmetry. Okay, so this defines also a cohomology problem, and they are equivalent. And again, the picture number can be arbitrary, only the ghost number has to be 0. And these formulations were used for defining, well, most of the superstring field theories that we are familiar with. But we can also use another version of the cohomology theory, of the cohomology problem. So we define this Q tilde as Q minus eta, and I'll use this Q tilde all the time. So just remember that it is Q minus eta. And eta here is just the 0 mode of eta, and they're both derivations, and they are anti-commute. And then in the large Hilbert space, at any fixed picture number, we can define this cohomology problem. A Q tilde on psi is 0, and delta psi is Q tilde of some lambda. And the picture is arbitrary, like before, and the ghost number is again 1 as before. But there's also something else that can be done. So we can take a range of picture numbers. Now, normally we would think that if you are taking some range of picture numbers, it would lead to several copies of the Hilbert space, of the physical states, whatever. And this is not the case here. And so we can take any range of pictures, and the cohomology problem does not change. The cohomology remains exactly the same as for a single picture. And the reason for it is that picture changing now becomes part of the gauge symmetry. And then in particular, one can attempt to take the limit of P1 goes to minus infinity, P2 goes to infinity, and include all the pictures, and in this way obtain a democratic formulation. Okay, but there is a subtlety here. Okay, so it's not trivial to take this limit. So what is the cohomology problem here? So how does it work, this a new formulation of cohomology problem? So this equation, if we take just a single picture number, then Q tilde psi equals 0 gives components, because we have the Q and the eta, so we have components at P and at P minus 1. And these components, because there are different pictures, they have to, say, vanish separately. So we have the equation Q of psi equals 0 and eta psi equals 0. So eta psi equals 0 means that psi is in the small Hilbert space. And then you have just the standard equation of motion, Q psi equals to 0. So this is the standard equation of motion. And the gauge transformation that we have is delta psi is Q tilde of lambda. So again, when we check the picture numbers, lambda must be a sum of two gauge fields which live at pictures P and P plus 1. And in order to obtain only component at picture number P, we have to restrict lambda 1 in this way and lambda 2 in this way. Now, because we work in the large Hilbert space, we know that eta and Q are both have a trivial cohomologies there. So we can write lambda 1 as eta times some lambda 1 tilde, and lambda 2 to write as Q times some other lambda 2 tilde. And then we take, say, the difference between this lambda 1 tilde and lambda 2 tilde, and we see that all in all, the gauge transformation can be written in this way. So we see that we got just the standard cohomology problem. What happens when we have a range of pictures? So now, as I said, changing the picture is just a gauge transformation. So for a fixed picture number, we can look at this equation. And if this, so this is the equation that must be obeyed in order to consider something at the cohomology. And then when these equations are obeyed, we can write a psi in this way as eta of something. So again, because eta is trivial in the large Hilbert space. Then we define lambda as xi times this new xi times psi, and then delta psi of this lambda takes this form. So x is the picture changing operator. So we see that we take psi and we remove psi, and we are left with x times psi. So essentially we change the picture. And similarly, we can also work, instead of with eta, we can work with q, and then we can define something which will give us an inverse picture changing. So essentially, we can change the picture of every state which is in the cohomology to any other picture number, and that's the reason for which we are left only with the standard cohomology problem. So what happens if we are taking just an unbounded range of pictures? So if the range is bounded, of course, we can just send all the components to any single picture. But when we have an unbounded set of picture numbers, then, and for now, let's ignore OPE singularities. I'll get back to this point. So x to the power of n is just the formal power of the picture changing operator. So when we define this operator, then a q tilde on it is 1. So this is a contracting homotopy operator. So as I guess all of us know by now, it means that the cohomology of q tilde is trivial in this space. But is it really trivial? I mean, what is really the definition of the space in which I am working? So what is the small Hilbert space and large Hilbert space? So when all pictures are included, we have to take some restrictions of the different picture components. So we have to essentially insist that we have something that decays as a function of picture number in order really to have to prevent something of this sort. And so it seems like a problem because we don't know how to really quantify this decay as a function of picture number. But is it really different from the standard problems we have with a proper definition of a small, large Hilbert space, small, large string field spaces at any particular picture? So in fact, we don't really have a Hilbert space. We say that we have a Hilbert space, but any mathematician who will look at what we're doing will say that we're just doing nonsense because it's not a Hilbert space and it is not even a well-defined space. So why it is not a Hilbert space? So formally it is quite clear, because the Hilbert space needs a positive definite inner product, and we don't have any canonical positive definite inner product. So we can say that, okay, we have something which is not positive definite. We have a non-positive definite inner product, which is defined by taking the expectation value of two states. But this is a very significant difference, because if we have two states in any algebra which in which we have something which is positive definite, then by the Cauchy-Schwarz inequality we have this, and then the sum of acceptable states is also acceptable, so we can really have a space constructed by requiring something like that. When we have something which is non-positive definite, then we know we can have two states which are, say, light-like, and the sum can be space-like or time-like, so it can be arbitrary. So the norm can be arbitrary, while the norm of two states is of the two states that I sum here is 0. So if we have something, if we are working with a finite dimensional space, this is not important. because we cannot say that, okay, I'm taking this A, and then I'm taking infinity times this A as a legitimate state, because we will not consider it as a legitimate state, because infinity is not a number. But if we have infinitely many such pairs of states, which say do not talk to each other, then we can build such a sum, and with arbitrary coefficients, of course. And now we can have still that the sums are zero, has a zero norm. So we will say that they are acceptable as states, but the series here, the sum of all of them, will have a norm that goes to infinity. So we have a problem with defining the space of string fields or of just vertex operators. Now, we know that our spaces can be decomposed into a finite dimensional spaces. So first, we can strip off all the momentum dependence. It just gives the standard conservation of momentum. Then we can just concentrate on a given value for the ghost number, the picture number, and the level. And when we do that, each such space is finite dimensional. But and then if we consider, say, just a single ghost number and a single picture number, then this is fine, but we still have infinitely many levels. So we will have this problem when we would like to define a spaces of string fields or vertices anyway. It has nothing to do with a democratic formulation, that is with removing the restrictions on pictures or not. So how can we still hope to define spaces when we have an inner product which is non-positive definite? So suppose we take some set of vectors which are well-defined, so they have some well-defined inner product. So this would be just all monomials of some a set of a creation operators acting on the vacuum at any given level, something of this sort. What types of linear combinations are we allowed to take? So we can say that we define a space, and maybe it's formally not a Hilbert space, but we don't care. And this will be the maximal linear space which contains all these vectors. So is this definition fine? I mean, is there really a maximal such space? And if there is a maximal space, is it unique? So there is a maximal space. This is by Zorn's lemma. We can define set inclusion as a partial ordering on sets of vectors. And then we take set union for obtaining upper bound for a chain with respect to this partial ordering. And then we know that there is a maximal space. So we can say that we don't have an explicit definition of the space, but spaces with which we can work are they still exist. But there's no reason to expect them to be unique, because we know that we do have states A, B, AN, and BN of the type that I mentioned here. So if I'm starting with a space which contains, say, only the ANs, then we know that we can that this space is fine, and we can extend it to something maximal, which includes all the ANs. And if we consider only the BNs, then this also works in the same way. But we know that we will get to different maximal spaces because we cannot have the ANs and BNs together. So this is a problem of defining our spaces. Okay. So we do not really have a Hilbert space. We certainly don't have something which we can call the Hilbert space, even when we fix the ghost number and picture number. Okay, so let's talk now about the old democratic theory, how it is constructed, and what are the ingredients of it. But before that, are there any questions so far?
I have one question.
Yes.
When you're discussing this O operator that realizes Q tilde.
Where was yeah, here, this one.
Yeah, this one. It has to be bounded in n equals 0, or it has to be from minus infinity to plus infinity?
No, it goes from 0 to infinity, the sum, the way it is written here. And you can also take another sum, which goes from minus infinity to minus 1, and then you will have two different contracting homotopy operators. So each one of them separately is a contracting homotopy operator. Okay? So if you take from minus infinity to minus 1, then you will not need this minus sign here.
Okay, yeah, I think I made a mistake.
Okay, any other questions so far? Questions at this stage are very important for me because these are questions that I might be able to answer. And it also gives me time to drink my coffee. Okay, so let's go to the formulation of the old democratic theory. So far I said, let's ignore OPE singularities, but of course, if we want to construct a theory, we cannot really completely ignore those. We have to treat them in some way. So the first component in the construction was to construct this multi-picture changing operator, and there are so-called potentials. So we know that we can have this O0 and O1, which are just the contracting homotopy operators for eta and for q. So these two operators are the reason why a q and eta are trivial in the large Hilbert space. And when we check what happens when I'm acting on O0, not with eta, but with q, and on this O1, not with they are the contracting homotopy operators, but when I'm checking what happens when I'm acting on them in the other way, so I'm acting with q on O1 and with eta on O0, then I get the x and the y, so the picture changing operator and the inverse picture changing operator. And then this structure of having potentials on which I can act with eta or with q, and I get from them various picture changing operators. So picture changing operator at x equals to 0 is just, p equals to 0 is just this x0, which is just the identity. So not changing the picture at all is very easy. But I can extend it to arbitrary operators which change the picture arbitrarily and are still well-defined. And not only well-defined, there will all be weight 0 primaries. Okay, so this was shown. But there are some problems here. So first, these operators are not uniquely defined. There's a very large freedom in defining these objects, even when we insist on having them as primaries. And the expressions are very complicated, and they are only implicitly known. So let's check some examples. So I mentioned so far O0, O1, and from which we can construct the x and the y. So let's check the other nearby operators. So O minus 1 takes a relatively simple form, and so G here is this standard expression here. And for O2, the expression is already much more complicated. And this thing in blue is just a particular choice. Now, this thing is something that lives in the small Hilbert space, so eta on it does nothing, but we need it in order to obtain a primary. So if we don't require these operators to be primaries, then we have even much more freedom, and then we can get somewhat simpler expressions. But we can have them also to be primaries, and the expression just got a bit more complicated. But if we would try to write O3, in this case, we will have 371 free parameters, which would lead, after you fix all the requirements, including the requirement of being primary, to a 94 parameter family of solutions. And in a particularly simple case, it will be the sum of quite a few terms. So you can have more terms if you want. So as I said, it is complicated and it is only implicitly known. So how to construct a theory? So we take C to live in the large Hilbert space, and we take any desirable range of picture numbers at this stage when we're talking about a linearized theory. And we want to take to have an action which leads to a linearized equation of motion. So this would be the equation that I'm after. For the reasons that I mentioned before, I want to reproduce my cohomology problem. So the action should be of this form. So we have the psi, q tilde psi, and the half, which we always have, but now we have to insert some operator here. Why do we need an operator? Because without the operator, we don't have a proper Gauss number, we don't have a proper parity, and this expectation value is evaluated in the large Hilbert space. So we know that this expression here should be even, and it should have Gauss number 2, and without O, we have a Gauss number 3 and an odd expression. So we need to insert here something. Now, if we insert it and we want to still obtain the proper equation of motion, we need to be able to pass this q tilde past this O insertion. Now, when we take all these requirements, so we know that if we do not, if we have just a general range of psi, it means that q tilde and O must commute. And also, we have to insert this O at the midpoints such that it will not be important whether it acts on the first or on the second expression. And this fixes O. So O is a midpoint insertion, and it takes this form, just a sum of all these potentials which I introduced. So if I'm taking just half of them, the upper half or the lower half, I'm just getting a contracting homotopy operator. If I'm taking the difference of these two contracting homotopy operators, I'm just getting a commutation, which is 0. Okay. Now, the equation of motion, which we formally obtain, is not q tilde psi equals 0, but O acting on q tilde psi equals to 0. But then we get back to the issue of what is the definition of the space of string fields. And we know that in the definition of the space of string fields, we should not allow any states which have supported the midpoint. Because if they have supported the midpoint and then we multiply such states, then generically we will get expressions which are divergent, and then they should not be considered as part of our space. So yes, sure, Nathan.
Once you fix the picture number of psi, I'm not sure what's going on. So when you say desirable range, you're saying psi has to be in a certain range. Is that right?
Yes.
So then you don't get the whole equation of motion O q tilde psi equals 0 because you're not allowing all pictures. So
yeah. So I'm saying
part of it.
So in the democratic theory, what I did, I just took all the range of picture numbers. I mean, all picture numbers from -infinity to infinity. And what happens if you take just a partial range? So at this stage, you can take it. And then in this case, you will not need all the O will not have to include everything because
no, I'm not worried about O. I'm not worried about O. So psi is constrained to be in a certain picture, right?
Psi is in some range of pictures, which can be a single picture, a range of pictures, all of them, whatever. At this stage, it can be anything. So,
so OQ tilde psi is also, the equation of motion you'll get from varying psi is also constricted to a range of pictures.
Yes.
So you won't get the whole equation OQ tilde psi equals 0. You just get a subset of it.
Okay, so if psi has some range, some finite range, then there might be some projector operator to some range of pictures acting on this equation. Yes.
That's right. That's what I'm saying. Okay.
Okay.
So it's not obvious that that implies.
Yes. So we'll have it later on. So in this original formulation, I essentially decided to use all picture numbers, and I had some reasons for that, and I will get back to this point really soon. So
okay, thanks.
Okay, any other questions? So the logic at this work was the following, as I said. because O has supported the midpoint and C is not allowed to have supported the midpoint, that if I fix any component at the midpoint, so I have some particular OP, then the component that multiplies it must separately vanish. And this means that each one of these components must vanish. So essentially, I am getting just this equation. And the fact that this equation and this equation are consistent, it relies on this understanding of the nature of the space of string fields, and on the fact that O is inserted at the midpoint. So this will be very different, of course, when we will try to generalize this. Okay, so this was the linearized theory, and it reproduces the cohomology problem. And now we want to extend it to a nonlinear theory. And this is, in a sense, straightforward. So we just add the interaction term, which is what you would expect the interaction term to be. And then using exactly the same logic as before, the equation of motion is the equation of motion that you probably expect to have. And the gauge symmetry is also extended in the way that you expect it to be extended. Now I'm not writing here the G, and of course, you can put it back if you want to, but it's really not important. So what about this criticism of problems with midpoint insertions of picture changing operators? So O decouples from the equation of motion. So the equation of motion has no insertions. So unlike, say, Witten's theory, which is singular because of that, then this theory has no such problems. And also it decouples from the gauge symmetry. So some other formulations, the modified theory, which had problems because you had midpoint insertions in the gauge symmetry, which leads again to string fields which are outside the support that they should have. So we don't have this problem again. So regarding problems with the midpoint, we don't have problems with the equation of motion. We don't have problems with the gauge symmetry, but we can have problems if we want to define a propagator. And if we want to do anything with the theory, then probably we have to be able to gauge fix and to define a propagator. And gauge fixing, because picture changing is part of the gauge symmetry, gauge fixing naturally would mean also fixing the picture, and then you would have problems. Yes, Nathan?
I think I'm going to ask the same question again. What is the range of psi? What is the range of pictures when you define the action?
So all of them.
Fixed?
Oh, no, not
all
fixed.
Of them.
Minus infinity to infinity.
So you have an infinite number of terms, so you're including all of them.
Yeah.
Okay, and the problem of cohomology doesn't come in because.
So okay, so
number one.
I said that you have a problem in any case, even regardless of having infinitely many, because of these issues with the proper definition of what we call a Hilbert space,
Okay.
which is Hilbert space.
Okay.
Of course. So now the criticism that I heard is that now the problem is more severe than what it used to be. Okay, and we will see if it is really more severe or is it just the standard problem. Okay. So in this case, you can still say that the problem is slightly more severe than what it used to be, because you have components at different pictures and you have different components, different types of string fields, which are not equivalent off-shell. So in this sense, the problem is slightly worse than of standard formulation. Yes, another question?
Yes, you said that equations of motion, there's no problem. So if I linearize the equations of motion and invert the differential operator, can I get the propagators in this way? So where I'm getting wrong?
So the problem is that you first have to gauge fix, right? And then, I mean,
yeah, I see.
And then you will have this O that you will not be able, you can take this O out and just say that it is equivalent to the equation without the O, without any projectors, when you take an unbounded set of picture numbers. Okay, if you fix the picture, then you can, by fixing the picture, saying I'm fixing a part of the gauge symmetry, I'm fixing the part of the gauge symmetry which is related to a picture changing by fixing the picture to be, say, -1, then you just get Witten's theory. And we know that this is inconsistent. So a possible interpretation would be to say that this is an inconsistent way to do a gauge fixing. And in particular, it would lead to a propagator, which is problematic. But then you should tell me, okay, that's nice. So what is a proper way to do gauge fixing of this symmetry, which is related to picture changing? And then I will just tell you that I don't know. So it's not very good.
Okay, thank you.
Okay, so I claim that these two problems are not there, but this problem is still there. Okay, so let's go back to the criticism which there is for this democratic theory, and we'll see what is the situation of it. So about the space of string fields, so the situation I claim is not much worse than for other theories. It is still slightly worse because of what I said, that in different pictures you have some string, some states, some string fields, which you don't have in some other pictures. And you don't know maybe how to translate it all to something which converges in some sense. So maybe it is slightly worse, but not much worse than for other theories. I mean, normally we don't really put much attention to this question of how to define the space of string fields because we really don't know how to solve it. But this problem is there. About the midpoint problem, so most of the problems which previous inconsistent formulations had are not there, but the issue of gauge fixing and defining a propagator, for this issue, the midpoint insertion is still problematic. Also, there is this issue of XP and OP that are only implicitly defined. Now, this is not horrible. This is maybe not ideal, but say for the closed string field theory, we also have vertices which are only implicitly defined, and but we know that they are defined, and if we need to go and find them to some given level, then in principle we know how to do it, and the situation is similar here. And these zero momentum operators of arbitrarily negative conformal weight are still there. So this is the situation as far as I see with regarding the criticism of this old theory. So is there anything else about criticizing this theory which I don't remember? Maybe someone can remind me something else if there is something like that.
Michael, I don't want to
Yeah.
remind you of any problems, but maybe you could remind me why we need a non-trivial OP. I just missed this point. Why just identity would not work instead of OP? Because then in the action, you could pick like the right picture number by combining the proper components of
Yes. So
size.
say I can have delta psi at some picture and the equation of motion at some other picture, and it's fine. I don't really need to have this O to have all these picture numbers. But the point is that in this case, I will not have this requirement that it commutes with this Q tilde.
But if you take identity, it commutes with Q tilde.
Oh, but identity does not have proper ghost number or parity. So,
but it will be taken care by the bracket, right? The bracket will pick the right ghost number and picture number.
No, I mean, include the physical states in the small Hilbert space, okay? But the expectation value is in the large Hilbert space. So you must include Xi as part of the definition of this O. And Xi is also consistent with the ghost number and parity that you need to put in. Okay, so you need to...
So you mean O contains the Xi zero mode?
It should include, well, it's not a zero mode because it must be a midpoint insertion, but the midpoint insertion includes
yeah, because otherwise without O the thing would be zero strictly.
Yes.
Oh, I see. Okay. Okay.
And then
thank
the
you.
moment you put this xi and you want to insist on that, then you are forced to this.
Mhm.
Okay?
Okay, thank you.
Okay, good. Anything else? Okay. So this was the theory. These are the problems with this theory. And we want to construct theories which will be free from these problems which are related to midpoint insertions. And so what do we want to do? So we want to, well, use the things that we know now that we didn't know at 2009 when I constructed this theory, that we can in some way smear insertions. Instead of using midpoint insertions, we smear something, and then we will probably have a structure which includes higher order vertices, but presumably this can be constructed. So we want to do something like that and define new theories with no midpoint insertions. And now we want to do it in the following way. So we define x and xi and y just the same way that we define eta to be just the zero mode of all these states. Of course, there's a big difference, which is the conformal weight of these states. So xi, for example, which we would see that it takes a role which is somewhat similar to that of q and eta, does not share with q and eta the property that it is a derivation. And this is a major problem, as we will see. But when we take these definitions and we just essentially work with zero modes, then we see that x and y, they commute. X is just the commutator of q and xi, and that's why x also commute with xi. So we will not have any OPE singularities, and we can now take powers of this, and we do not really need now all this OP, which we defined implicitly, and the XP, which we defined implicitly, and we will try to construct everything in terms of this. And of course, we know that we can also put some functions here and maybe generalize the construction that I'm presenting here, and maybe it will help in some way. Also, maybe if we just plug some function here, we can take a limit which will bring us back in a singular way to the all democratic theory. So that's the idea of what we want to do. So what are the challenges now? So x and y now are regular, but we know that they have kernels, and we have to do something about it. And y is the inverse of x, but it is the inverse of x in cohomology. It cannot be its inverse generally because they have kernels, right? And a third important challenge is that now the equations q tilde psi equals to 0 and O on q tilde psi equals to 0 are no longer equivalent. Because, as I said, the major ingredient that I used in order to say that these two equations are equivalent was that O has support at the midpoint. So the question is now, how can we remove this O? Is there an inverse to this O? And this will tell us that it is a problem to do it when we have a fully democratic theory, because there is no really inverse to this full O, which includes all pictures from minus infinity to infinity. And this suggests that maybe we should not take a theory which is completely democratic, but maybe take something which is only pseudo-democratic. So in order to take care of these problems of kernels and the inverse only in the cohomology, we suggest to do the following thing: to restrict the space of string fields. This was done in several other contexts before. And we want to do it here now for the current theory, which includes only a Neves-Schwarz sector. So we want to consider only string fields which obey xy on psi equals psi. And in our case, xy and yx is the same thing because, as I said, they commute with this definition. Now, xy is not a projector, so it seems a bit unnatural maybe to do something like that. It's not a projector because not all its eigenvalues are 0 and 1. So for example, we evaluated just this state. This state is not important in any way, just something which we could easily calculate. And we saw that this XY operator has also 4 as an eigenvalue. We also managed to find -3 as an eigenvalue, and presumably there are many others. Of course, this XY might not even be diagonalizable. Again, if we were working in a situation where we have a positive definite inner product, then this XY must have been diagonalizable, because it is a symmetric operator, but now it does not have to be diagonalizable. But it seems to us a bit unnatural to expect it not to be diagonalizable, at least over physical states, although we cannot rule it out completely. And also, if there are some problems of this sort, then presumably adding some function here in the definition of x and y that is taking not exactly the zero mode might improve the situation. So, but we know that physical states, they must have a eigenvalue 1 of this xy. So we define a restricted space of string fields, which is the space of all states with eigenvalue 1, and we assume that at least for these eigenvalues there are no non-trivial chains, so everything is diagonalizable, and then we say that we consider just this space. And because in this space we have all the physical states, then considering string fields which live in this state seems to be good enough. And moreover, because now we have the x and y, they just give us isomorphism between states with different picture number when we restrict to this space, then now we have this isomorphism not only at the level of the cohomology, but already at the level of the chains. And in particular, because there are no zero momentum negative conformal weight states for p equals -1 or 0, then we don't have such states at all now. So this problem is automatically solved when we consider this state age restricted. The next question that we ask ourselves is, what is the possible range of picture numbers? So before that, I just want us to know that in the all democratic theory, despite the fact that it looks democratic, it is not really democratic in the sense that the moment we add the interaction, p-1 and p0 become special. So if we take some given fixed picture number, which is not -1 or 0, then we know that the equation of motion, which is supposedly a q tilde psi plus psi square equals 0, it contains this psi square, and the picture of psi square, you cannot find it inside the term with the q tilde psi. So you must have psi tilde square to 0, and this seems to be too restrictive. So in this sense, if you have a string field which has support at some picture which is not 0 or -1, it would normally have in the all democratic theory all picture components up to infinity or up to -infinity, and maybe even both, but at least one of those. So let's see in the current case what is the restriction of possible ranges of picture numbers before we try to construct a theory. And okay, so similar issues are true also when we consider the gauge transformation. So what do we have now? So we know that we can take psi and lambda to be completely unrestricted, and then we just get a full democratic theory. And I remember that when I constructed it, so Nathan, you told me that why are you taking all picture numbers and not just half of the infinity of picture numbers? And I told you that it is impossible for some reason, but it seems now that it's not impossible. I don't know why I said it. So you can also take the picture number of psi and lambda to go only half the way to infinity. So start at -1 or at 0 and go all the way to infinity, or all the way to minus infinity. So here only half the states can contribute. So we call this a theory a pseudo-democratic. I mean, assuming we can construct a theory, of course. Then this is pseudo-democratic. Only half of the states contribute. And we can just change there is a symmetry of changing the roles of Q and eta, so this is related to that. Another option would be to take psi to have only these given values of -1 and 0 to allow changing the picture from -1 to 0 and changing back from 0 to -1. And in this case, it would be enough to take lambda with only picture number 0. And there is a nice decomposition of the equations of motion and of the gauge symmetry. And it looks very attractive. And presumably, if you can construct such a theory, it would be very natural to add to it a Ramond field at picture number -0.5. And well, we did not look into it further, although it is very tempting to do it at some stage, because we were looking for something which is really, if not completely democratic, then at least pseudo-democratic. So we looked at these options, and they are all the same up to some symmetries, so we can just choose one of these options and work with that. So what do we try to do? And I will not say that we construct it, because you will see that we face some problems with the constructions, but at least what is it that we are attempt to construct? So we take a range of string fields, which is only half infinite. And in this case, we can take as O this expression. And why? Because other components of the O that we had before will not contribute when they are inside the web. So formally, Q tilde and O tilde is -1, but when you remove here Q tilde and O tilde, you remain with this psi squared. Psi squared has a picture number which is -2 or less, so it cannot contribute, so we do not care about it. So it is the same as if it is 0 when you consider this restriction of range of picture numbers. So the equation of motion now, when you take the variation of this action, so now you do have, as Nathan suggested, this projection over a range of picture numbers. And the gauge symmetry now contains two parts. So you have the gauge symmetry, which you expected to have, and now you also have this gauge symmetry, which is Xi acting on some other state. And the second gauge symmetry, it can be used to send psi to the small Hilbert space. Now, the question is, of course, whether this equation is equivalent to the equation without the O, although here formally O appears. Now, it can seem that the simplest way to do is just to act with Q tilde on this O and to use the fact that it gives you identity, the commutation, and then you just get the standard equation, but Q tilde does not commute with the projection. So you can still do that, but you will not remove everything. But anyway, you can just check this equation and this gauge symmetry and see what does it imply. So as I said, you can first remove all the components in all the upper components of the large Hilbert space and have psi to be in the small Hilbert space. Then when you set lambda for every given picture number to something like that, then you get delta psi. You can change the picture of psi. So you have now picture changing even off shell, okay? But that brings you back to this upper component of the large Hilbert space, but you can remove it again. So you can eliminate this second term. So now you can send all the components from any given picture to a particular picture, which can be, for example, -1. Now, in this way, you can get presumably some sums which will not converge. And you can say, okay, it's a problem. You have sums that do not converge. But in fact, you can invert the logic and say that if by doing this, you will get to any sum which does not converge, does not even absolutely converge, the meaning of it would be that you are just working with a string field, which is illegitimate. So the requirement of having a legitimate string field would be that any component, when you transform it to any given picture number, when you squeeze all the infinite range of picture numbers of a particular component to a given picture number, you must have a sum which is absolutely convergent. And now, because there is isomorphism already at the level of chain, so already at the off-shell level, then for each finite dimensional space of fixed level, you can bring all the pictures, and the requirement here is very simple, very natural. And then you just get a state which is concentrated at a given picture. So essentially, now there is no difference whatsoever between the problems that we have with defining of string field spaces for a fixed picture number and defining these spaces for the current construction. Okay. So after we are doing that, we have something which lives in the small Hilbert space at a given picture number. And now we see that we are left with a residual gauge symmetry, which is just the standard gauge symmetry. So we see that the equation of motion, the gauge symmetry that we have, are equivalent to the standard cohomology problem that we have in the small Hilbert space at any particular picture number. So this means that we really managed to achieve what we wanted to achieve. So to get a proper form of the linear gauge transformation and a gauge symmetry. So, okay, so I already said that. So we're left only with standard problem of defining a Hilbert space at a fixed picture. So nothing more than that. So let's consider again at this stage what can we say about the criticism of the theory. So what about the space of string fields? So now the situation is not almost as good, but it is really as good as in any other picture, as in any other theory, because we have this isomorphism already off-shell, because of the projection to this restricted space. There are no midpoint problems because the midpoint does not enter the construction at all. Zero momentum operators, they are on God. This problem does not exist anymore. The problem with operators which are only implicitly defined, so I said it's not such a big problem, but anyway, it is absent now because we just have powers of x, and there's no problem in defining these powers of x because it is a regular expression. So it's just taking a contour integral around the contour integral, etc. And a gauge fixing and defining a propagator, at least when we look at this theory, which is free, it seems to be straightforward. So no problems remain, except of course, that this is only the free theory, and the real challenge is to extend it to a non-interacting theory. So questions so far? Okay. So how to add interactions? So the first thing to do is to check what are the gauge symmetries that we have. And presumably the gauge symmetries that we have will also obtain some corrections when we go to a nonlinear level. And there's always the question of whether we should extend all the gauge symmetries that we have, or maybe we should fix some of the gauge symmetries and then extend only the other ones. So let's first see what are the gauge symmetries that we have. So of course we have the usual gauge symmetry that we always have. Then we have the picture changing, and picture changing is just part of our gauge symmetry. So this is another component of the symmetry that the gauge symmetry that we have. Also, there are other components of the gauge symmetry which is related to Xi other than those which are related to picture changing. And also there is this issue of projection to this restricted space, which can also be interpreted as a gauge symmetry. Yeah, Nathan.
Sorry, I got distracted, but so you're restricting to just certain pictures. Which pictures? Can you just remind me? So just the free theory.
Yeah, so I say that we work in this range of pictures from -infinity to -1.
And so what if you just restrict to the massless? Just simplify. What does the action look like?
So you essentially have an action which includes the standard terms that you have for -1 and copies of the same thing for other representations of the picture of the same thing with a symmetry which relates these equations.
No, so it's a gauge symmetry. So only one of them appears, right? You can't have all of them.
Yes.
So you get.
So if you add to this construction the requirement that at any particular state, physical or not physical, the sum of, say, absolute value of the components at all different picture numbers is convergent, then this is just equivalent to the standard problem, to the standard expression. And you can just gauge transform everything to picture which is -1.
So you have an infinite sum, right, over terms. So first of all of the pictures are negative, right?
Yeah. But
So
as I said,
only
it is you can as well take all the pictures to be positive. It will.
No, okay, fine. I don't care either way. But then the insertion has all. Let's say you choose them to be all negative, just to be explicit. The insertion that you're putting has all positive pictures.
Exactly.
Okay?
So this is the insertion that you put.
So you're going to get an infinite number of terms that, right, from each term in the insertion is going to give you a contribution.
Yes.
And the claim is that that theory is invariant under gauge transformations which eliminate all of the states except for one.
Yes. So this is the algorithm that you can follow in order to bring everything to the small Hilbert space at picture -1, and you are left with in this space just with this gauge symmetry.
So even though the insertion does not commute with Q tilde, it's still okay.
Yes, because they not commute in a picture which does not contribute anything to this expression.
Okay, go ahead. I think I follow. Okay, thanks.
Okay, so how can we construct an interacting theory, or again, maybe I should say, how can we attempt to construct an interacting theory because we did not really manage to get there. So there's these gauge symmetries, and the question is what should we do with each one of them? As I said, that the projection to the restricted space can be interpreted as a gauge symmetry because we can just if you just give me any string vertex, I can just put on each entry of this string vertex just the projection to this space, and then everything else just gives a zero contribution. And as I said, everything else does not include anything physical, and then all the rest is because it does not contribute to anything, and then it is just gauge degrees of freedom. So, but we can also say that we really work inside this restricted space. It's a linear space, so this is also fine. But of course, we can also think that maybe we should think of it as a gauge symmetry really and attempt to add some nonlinear terms to it. And then we will have to work not inside the restricted space, but inside the whole space. Okay, so the challenges here are that, okay, Xi is not a derivation, as I mentioned, and we have a gauge symmetry, which is related to Xi, and this is really a significant obstacle for the construction. And we attempt several directions of what to fix, what not to fix, and I will not mention all these directions here, just one. So, okay, other than this trivial, which I will mention now. So there is a very simple way to construct an interacting theory. So because at this linearized level, we say that we can just send everything to picture -1 and picture changing is really a gauge symmetry. Then we say, let's keep this changing and C symmetry as exact gauge symmetries. And then you give me a string field with all negative components. What I'm doing with it is just send everything to picture -1. And then I have an action for states at picture number -1. So EKS, for example. And of course, it will not be exactly EKS because I'm working here with this restricted space, but essentially it will be the same. And this projection commutes with everything else. The theory will just be the same, it will be consistent. The only thing that this theory will not really be essentially democratic in any way. And you will say, and rightfully so, that I just found a very complicated way to write something which you knew before already how to write. So what we want to see is whether we can have some construction which would be really essentially democratic. So we will use will not use more projections to a given picture number than needed. So if the equation of motion tells us that we have to use a projection in some way, then okay, but we'll try not to use that as our construction. So what do we do here? So the first thing is to rewrite the S2 that we had as some omega of Q tilde psi and psi. So omega, it is not a symplectic form because there are also gauge degrees of freedom here, but presumably after you fix them, this will give you a symplectic form. And this omega we define in the before as the free. So omega is defined as OA with B. So I'm putting the comma here to distinguish the two insertions now. And this omega is symmetric because this O, as I mentioned, it has nice BPZ property. And what we want to look for an off-shell extension, which will use this omega in the construction. So I want to have S3, which looks like a third of this omega of psi and M2 of psi psi. And now M2 is the Witten star product, which I left implicit before, but now I want to write it explicitly because we would have to generalize it in some way. And this is the form of the action that I need to impose when I'm considering the small space states which are physical, because then I will get all the interactions properly, regardless of the value of the picture of the different components of psi. Okay? So I want to have something which will generalize it. So why do I really need to generalize it? What's wrong with that? So the point is that we have this O as part of the definition. So this O includes the Xi and includes powers of X. Now X, which is the picture changing operator, we can move it around as much as we want to any point as long as we are talking on on-shell states. But now we need to have also off-shell states, and then we will not be able to move these powers of X to arbitrary positions. So this term, we can say that the O acts here or here or here, and it gives us this, but only for these on-shell states. So this is the utilization. So we want to find some M2, which will take when we put in these M2 states, which are on-shell and are at the small Hilbert space, it will reduce to this standard Witten star product. But we want also this M2 to be compatible with this omega, so we want to have this cyclicity property. And for the standard reasons, because if you impose it and you define S3 to have this form as is natural to do, then the delta of S3, you can write it in this way. So you will have delta psi and M2. So you will use cyclicity in order to put the delta psi in one place, and you will just be left with this M2. And then the equation of motion that you get from the reaction together with this S3 will have this form, which is sort of what you would expect. And so this is the idea. So the question now is whether we can find this M2. So as I said, we want essentially to be able to move around this O insertion. And the point is that in omega, we have this O and at some given place. So the first thing that we have to put in this M2 is something that will kill this O. And then we will be able to move it to some other places. So I want to have this R here as the first thing. Now it will act, it will also have some nice BPZ properties. So it will be able to act with it on the other state. And so it will just kill this O. So I want to define an R which commutes, anti-commutes with this O. And also we want this R not to contribute when we act with it on physical states. So this seems like a lot of restrictions, but in fact, there are many such possibilities for choosing such R. So we can choose just this minus Q tilde, and this would be a nice definition of this R. But we can also take Y minus 1 times Q, or 1 minus X times eta, or combination of such expressions with sum of coefficients equal to 1. This still all holds. There is an added nice property for this choice, because Q tilde is a derivation, but this expression and this expression are not derivations because Y and X are not derivations. Okay, but at least for now, it is not important, and we can take any R that obeys this property and is on-shell small Hilbert space states. So the problem is that so the definition of this vertex, so I'm writing here M2 and a 1 because I'm attempting a perturbative construction. So this will be the first part of M2. And this is what you would expect. So first, remove the O, and then put a third of O on the left state, on the middle state, and on the right state with some proper powers that comes from parity. And parity here is just the usual Grassmann parity. So we did not attempt to identify any infinity structure or anything of this sort. So of course you can change the definitions of parity if you want to do that. So anyway, when we plug that into the action, then some algebra shows us that the vertex is not quite cyclic. And we have to add to the vertex a second part. And we add this part. So you see in this second part, R acts on a state here and here and here and here. In the second line, in fact, we have one more copy of R, but then we also have one more copy of O. And what it means is that when you plug here physical states, then this vertex just gives you 0. And when you plug now this additional component to the expression and require the cyclicity property, then you see that all the problems that you had from this part disappear, but new ones appear. And in order to remove these new ones, then you have to add one more contribution. And again, you have R acting on the state. So again, this part of the vertex will not do anything to physical states. And now when you add that, you have the cyclicity, and then you get the equation of motion in the form that you wanted them to be. And one more remark is that we have now here O squared here and here, and other than the Xi insertions, you basically have 1 over 1 minus X squared, but 1 over 1 minus X squared makes sense. So this is an expression which you can work with, and when you consider any given picture number, you have a finite expression for your components. If we were trying to do the same with a fully democratic theory, then we would have just an infinite sum from minus infinity to infinity of powers of this x, and that would make no sense, because when you square such a term, you just get infinity times any given picture number. Okay, and of course you can add also to the vertex one more piece, because you have this O. This O as here as a definition of this omega, then if you put a vertex which also includes an O or a XC with some other components attached to it, because C squares to 0, then this will not contribute at all. So you can add this, but it will change completely nothing. So we ignore it for now. So this is all nice, but the problem is that we also have to identify a gauge symmetry. So in order to, so the idea is that we would expect to have a higher order contributions. So we want the gauge symmetry to close only up to the current power of G, which we did not write, etc. So it means that we have to identify some delta 2 of psi, which will obey this equation. So here is the delta 1, the linearized gauge transformation, and we plug here the M2. And here is the delta 2, which we are looking for, and this is the linearized part of the equation of motion. So the question is, what is delta 2? And of course, the natural guess might be to say, okay, just write the standard expression, only instead of Witten's product, just write M2, capital M2. But this is an unacceptable expression. Why is it unacceptable? So there are many reasons, actually. But the most obvious one is that it gives you a picture range which is unacceptable, because in the definition of this M2, you have all these powers of O. So for on-shell states, this all dies. But for off-shell states, you just get components with higher and higher picture numbers. So this cannot be a part of a string field, which must not exceed -1 as the picture number. So we saw that from the one hand, it is better to work with a pseudo-democratic theory. But then now we see that it gives us problems, because if we would have worked with a fully democratic theory, then there would be no problem in considering something like that. But now it is an unacceptable expression. So we have to see what can we say about the gauge symmetry anyway. So we work with these terms, and we try to see what is the result of this requirement. And after some algebra, and in this algebra, many expressions just cancel out very nicely. And we just get lambda, which multiplies this, which is the M2. This is the Witten's product of Q tilde psi with psi. So if it was only for this term, then we would say that we just have really the completely standard expression for the gauge transformation, which would be really great. But the problem is that we're left with one last piece, which we do not know what to do with it. And this is really the biggest problem with this construction, because it seems that we do not know how really to define the closure of the gauge symmetry, even to this lowest non-trivial order that we try to do. And as I mentioned, we try to do some other things with other approaches with choosing which gauge symmetries to fix and not to fix, and we faced similar problems. So you can say that, okay, I essentially wasted your time, because after all the construction, you get something which still you don't manage to close. But maybe this is not quite the case. So let's see what we managed to do and what still should be done. So what did we do? So first, we identified directions towards the construction of new theories. We saw what is the possible range of pictures, etc. We saw that it's probably useful to work with the projection to this restricted space. It solves some of the problems that you face with democratic formulations. And we identified the linearized gauge symmetry, etc. And for the free theory, we essentially addressed all the criticism that there is on a democratic formulation. But there are problems. So the biggest problem that as I said, is to resolve this problem with the gauge transformation. Another issue is that the expressions that we got are not as elegant as the original democratic theory. So the original democratic theory was cubic and straightforward, and you could use this structure, as I said, to naturally add Drummond fields to the story and to naturally extend it to a classical master action. But now everything seems much more complicated. And well, okay, if you have, say, general relativity or an infinity structure, and you take only few first components of it, it will also look like a horrible mess. So I think that the big problem here is that we do not know what is really the mathematical structure that lies behind all this story. And presumably this mathematical structure is really relevant for understanding what is the really big symmetry principle behind string theory, but maybe I'm exaggerating here. So what else should be done? So we should probably attempt to identify the structure that would lead us beyond the cubic level. And we should, as I said, resolve this issue with the gauge transformation, and there could be many directions towards it. And from what we saw is that the more gauge symmetries that you try to fix in this construction from the beginning, the more problems you would have. So what I suspect is that the fact that we assume that the gauge related, the gauge transformation, which is related to Xi, does not obtain any corrections, this is really the source of the problem, and there should be some correction of this form. And but I remind you that we did not really attempt, I mean, we attempted, but did not manage to get very far. Did not manage to construct something like that, is that because Xi is not a derivation. And this really complicates the whole structure. And presumably, in order really to build a theory now with the Xi obtaining corrections, you would have to have some non-associative algebra. And I think that this is a very hard problem. And okay, another interesting thing is to know the following thing. So as we said, if we don't put any restrictions on the space of string fields, then formally Q tilde has a trivial cohomology in this space. And Xi, of course, it has trivial cohomology because it just squares to 0. But then we can say that in this very large, extremely large Hilbert space, huge Hilbert space, we have two derivations with trivial cohomologies, Q tilde and Xi. But we already had something like that because we had the Q and eta in the large Hilbert space. So algebraically, it is a similar structure. Again, except for the fact that Xi is not a derivation. And then one could try to combine this Q tilde and Xi and construct something which will be, say, maybe a non-associative analog of Berkovitz theory or or a similar extension of the democratic theory. And this might be an interesting thing to try to attempt. But again, probably a very complicated thing. And the last thing is that I remind you of this theory, which had components only at -1 and 0, and to construct a theory with these components when changing them is a gauge symmetry, then I think that this could be really a nice thing that could be very useful. So that would be all. Thank you.
Thank you very much, Michael. Very good time management. Do we have questions? I will stop the recording so people can ask freely.